We saw that pipelines can have three kinds of hazards: structural, data hazards, and control hazards. This video is about the second kind of hazards, that is data hazards, why these occur and what we can do to get around these hazards. Data hazards happen when there is dependence of data across instructions which pass through the pipeline. Such data dependence can be in register locations or in memory locations. A dependence essentially means that one instruction produces data which is used by another instruction. In the other examples of pipelines we saw, such as say the bicycle manufacturer, it is quite difficult to imagine a scenario where one unit of work, that is one bicycle, depends on another unit of work, another bicycle. On the other hand, in the MIPS pipeline, it is very natural to have one instruction dependent on another instruction. In fact, any meaningful program by its very nature will have such data dependence. For after all, if all the instructions which executed were independent of one another, then the program would not be doing anything meaningful. Let us take this example here to understand data dependence across instructions. In this example, I have used the deluxe instruction set. Deluxe, which is written as DLX, is a simplified version of the MIPS machine. Its instruction set, its architecture, and its implementation is all very similar to the MIPS we have looked at so far in the course. I am using Deluxe here instead of MIPS just because it is far easier to write R1 rather than $S0, $T1, and so on. The registers in Deluxe are numbered 0 to 31, R0 to R31. So here in this instruction sequence, we have first the add instruction, which adds R2 and R3 and stores the value onto R1. Subsequently, the subtract instruction uses the value in R1 for further operation. Similarly, the remaining instructions as well, AND, OR, and XOR, also use the value of R1 produced by the first instruction. In other words, all the instructions after add depend on R1, which is produced by the first instruction. While it is natural to have dependence across instructions in a normal program, pipeline does not like such dependence. So if we try to use the normal pipelining for this sequence of instructions which we just saw, this is what the pipeline timing diagram will look like. These are the 5 stages of the MIPS or Deluxe pipeline. Let us say we start execution in clock cycle 1. I will denote that as CC1 here. So at the end of clock cycle 5 is when the value of R1 will be written back to the register file. However, if we proceed with the normal mode of execution of the pipeline, then what will happen is that the register read for the subtract instruction is happening right in clock cycle number 3. Likewise, the register read for the AND instruction will happen in clock cycle number 4. The register read for OR instruction will happen in clock cycle number 5. All of these are invalid because they use the old value of R1, whereas the programmer has intended that the value of R1 produced by the add instruction, which is available only in clock cycle number 6, should be used. So in this example, only with respect to the XOR instruction will the result be correct. For all of the other instructions, the normal pipeline execution of the program will produce the wrong result because we are using an old value of R1, something which the programmer did not intend. If you think a bit, bring back into your mind the pipeline data path and think, you will realize that this problem is happening because of the write back happening in the 5th stage, carrying information back in the pipeline to the register file. So this backward flow of information in the write back cycle is the fundamental reason for these data hazards. Well, what can we do? One simple solution to have correct program behavior in the presence of such data hazards and with pipelining is to stall the pipeline. So in this example, we will have to stall the subtract instruction until it is pushed all the way to clock cycle number 5 so that the reading of the register will happen in clock cycle number 6 when it will be the correct value of R1. So we have to stall for as many as 3 cycles in this particular example if we use the stalling solution. So the question is, can we do better than stalling for as many as 3 cycles? The answer is that we can indeed do a whole lot better than stalling. The first part of the solution lies in arranging the register file so that reads happen after writes in the same cycle. That is, we are going to arrange such that writes happen in the first half of the cycle and reads happen in the second half of the cycle. So if you look at this pipeline timing diagram, which I have drawn slightly differently by showing a simplified version of the data path itself, showing the different modules and the latches in between. Here in clock cycle number 5, what will happen is in the first half of the cycle, the register file will be written in the write back stage of this add instruction, and this OR instruction, which is in ID stage right now, the second stage, it is going to read the value of R1 in the second half of this cycle. So with respect to this particular instruction OR instruction, we have indeed read the correct value of R1, which was produced by add by arranging the register file such that writes happen in the first half and reads happen in the second half. To show this, I have drawn an arrow here which indicates that the value written in the first half of this cycle will be what is read in the second half of this same cycle. Of course, this solution does not address the other 2 data dependencies. To address these, we need to do something more. Now let me here number these instructions. Call this instruction number k. This is instruction number k plus 1, k plus 2, k plus 3. We saw that if there is a dependence between k and k plus 4, we don't need to do anything special. If there is a dependence between k and k plus 3, that is resolved by arranging the register file such that writes happen in the first half, reads happen in the second half. Now to address the dependencies between instructions k and k plus 1 or between k and k plus 2, we need to do the following. Let us first focus our attention on this instruction k plus 2, which is in this case the AND instruction, which is supposed to use this value R1 produced by instruction number k. If we look at this AND instruction, we realize that the value for doing the AND operation is really required only in its third stage, not in the second stage. Although in the usual mode of execution, the value is read in the second stage, we actually need it only in its third stage. And then we realize that the data which is required for doing this AND operation is already available. It is available somewhere. It is yet to be written to the register file, but it is indeed available. This add operation has completed in clock cycle number 3, and at the end of clock cycle number 3, it would have written that value onto this latch, which would have passed on to this MEM write back latch by the end of clock cycle number 4, and in clock cycle number 5 is when we need this value of R1 for instruction k plus 2, which is available. This value is available in this MEM write back latch, ready to be written to this register file. It's just that it has not yet been written. But the fact that it has not yet been written should not affect what we want to do. We want to get this value of R1. So we forward this data from this latch to this location where it is needed. This mechanism goes by the name of data forwarding because the data which is yet to be written to the register file is forwarded before it is being written to the register file to a location where it is needed. And in this case, the location where it is needed is in the EX stage. Now we are yet to handle the dependence between k and k plus 1. It turns out that nothing special is happening. Very much similar thing is happening as in the case of dependence between k and k plus 2. For the sub instruction, we need the data in its third stage, which in this example happens to be clock cycle number 4. We realize that the data which is of course yet to be written to the register file, is available in this EXMEM latch by the end of clock cycle number 3. So this value is forwarded from this latch before being written to its register location to a location where that value is needed for ALU operation for a subsequent instruction, in this case instruction number k+1. So this is another case of data forwarding, this time from a different latch to the same location in the data path, that is just before the ALU. So if we have these two kinds of data forwarding, that is from EXMEM latch to in front of ALU, and also from MEM write back latch to in front of ALU, as well as having arranged the register file to write in the first half, read in the second half, we see that in this particular example, the data hazards are all taken care of. We don't need to do any stall at all. In other words, despite the data hazard, despite the data dependence, the pipeline will proceed without any stalls, without wasting any time. There is a price though to pay for this efficiency, that is in terms of pipeline control, that we will look at later. In the examples of data forwarding we just saw, all of the data forwarding happened to the EX stage, that is just in front of the ALU. There is one scenario where we may have to do data forwarding to the memory stage. Can you think of which instruction may need a value produced by a previous instruction in its MEM stage? Well, the store word instruction requires the register to be stored. That value is really required only in the MEM stage. So in this example, we have a load word instruction which loads a value onto R1, which is stored onto another memory location. So in this store word instruction, the value of R1 gets stored onto a particular memory location. This has a data dependence with the previous instruction, and if we do not do forwarding, we will require stalling. A question to you is, suppose we do not do any data forwarding, how many cycles of stall will be required for this store word instruction? Well, it will require 3 cycles of stall if we had a register file without the read after write arrangement. If we had a register file with the read after write arrangement, it will require 2 cycles of stall. But of course, with data forwarding, we do not need any stalls at all. As shown in this diagram, we can forward the data from this latch. The value which is needed in the 4th stage, the MEM stage of the store word instruction, is available in the MEM write back latch. This store word instruction enters its 4th stage in clock cycle number 6 in this pipeline timing diagram, and in clock cycle number 6 the value which is needed is available in this MEM write back latch. So we forward this data directly to the location where it is needed, that is in front of data memory, before the data goes through the register file. Of course, the same data is also written to the register file, that is the normal operation, but that is not relevant here because we are focusing on the data forwarding which happens from this latch to the location where it is needed in front of the memory. Now there is another instance where data forwarding may be needed to the MEM stage, that is shown in this example. In this example, the first instruction is add followed by a load word which is not dependent on any instruction, and then there is a store word whose data to be stored is dependent on 2 instructions prior on this add instruction. Suppose we do not use any data forwarding, how many cycles of stall will be required for this store word instruction? We require 2 cycles of stall if the register file did not have a read after write arrangement. If the register file had a read after write arrangement, we will require 1 cycle of stall. Now think and tell as to how we can avoid this stall by using data forwarding. Well, it turns out that we really need this data in clock cycle number 6, that is when the store word instruction enters its MEM stage. However, in clock cycle number 6, the instruction which produced the data is no more in the pipeline. So what we need is yet another latch which will carry the data to be forwarded after the fifth stage of this instruction that I'm going to call as the post write back latch. And from this latch, we need to forward the data required for this store word instruction in front of its memory. We have so far talked about data dependence in register locations. That is, one instruction writing to a register location which is needed for computation in a subsequent instruction. Now the question is, can a similar dependence happen with respect to memory locations as well? That is, can there be a data hazard with respect to a memory location? What do you think? Well, in the case of the MIPS architecture, such data hazards are not possible. Memory data hazards are not possible. This is because the way the pipeline stages are organized, the memory operations always happen in the fourth stage. That is, data memory operations happen only in the fourth stage and the instruction memory is anyway read only. Of course, if we have an architecture where there is a self-modifying program and data and instruction memory are the same, then memory data hazards are also possible. Memory data hazards are also possible in architectures which do direct computations on memory locations. Of course, MIPS does not support that, so there is no worry of memory data hazards in MIPS. To be more explicit, suppose we have a store word instruction which stores a register to a memory location, let me call that X, and then a subsequent instruction loads that value X onto some other register. There is a dependence from this instruction to the next, memory data dependence. However, there is no hazard because the MEM stage of this instruction load word is guaranteed to occur after the MEM stage of this instruction store word. That is, memory operations always happen in the order of execution of instructions in the MIPS 5-stage pipeline. Data hazards actually can be of three types. The first type is read after write hazard, and that is the kind of hazard we have been seeing so far. So in read after write dependence, the read of say register R1 is supposed to happen after the value of R1 is written by a previous instruction. And if this is potentially violated, if this order read after write is potentially violated, that's called a RAW data hazard situation. We can also have a write after write data hazard. Now in the MIPS pipeline, the write back happens only in the fifth stage. So in the MIPS pipeline, write after write is not possible. This is because just like in the case of the MEM stage happening in the order of execution of instructions, the write back stage also happens in order in the MIPS pipeline. So there is no possibility of write after write hazard. However, in other pipelines, it is possible that there is a write after write hazard as shown in this example. In this example, I have assumed that there is a pipeline which has potentially 6 stages for the load word instruction, with the write back happening in the 6th clock cycle and the register instruction add having only 4 cycles. So potentially this add instruction which follows in the program, the load word instruction, completes sooner. So if this happens, we see that there is a write after write hazard. That is, the wrong value gets written onto R1 in normal execution of the pipeline. In normal execution of the pipeline, the value which gets written onto R1 will be that produced by this load word. However, what the programmer intended was the result of this addition. This kind of an out of order write is called a write after write hazard. Well, if we have different instructions taking different number of stages in the pipeline, this will create other problems as well. For example, it can create structural hazards. Can you think of an example where a structural hazard can happen because different instructions complete in different number of cycles? The third kind of data hazard is write after read data hazard. In this write after read, the dependence in the program is that write should happen onto a register location after read. So for example, Here I have shown a store word instruction followed by an add instruction. What the programmer intended was that the store word should use the value of R2, which was before the value written by this add instruction. So that is, the program dependence is write to R2 should happen after read of R2. This WAR hazard also is not possible in the MIPS pipeline because reading happens early in the pipeline, that is in stage 2 itself, whereas writing happens in stage 5. So this write after read dependence can never result into a write after read hazard. However, suppose we had a pipeline where, let us say, the store word instruction read the value of R2 just before its MEM stage. And in this example, we also imagine a scenario where the memory access is broken up into 2 different stages, so that the store word instruction takes 6 cycles, whereas the add instruction takes until clock cycle number 5. And if we also had the register file arranged such that write happens first and then read happens, we will see that the store word will read the wrong value of R2. So it will read the value produced by add, assuming that the value is read in clock cycle number 5 in the MEM2 stage. As we can see, there is a lot of ifs which we have to put together to create this write after read hazard. It is indeed quite rare in any architecture. Now, like a good computer scientist, if you are thinking, well, there is read after write, write after write, and write after read. What about read after read? Well, read after read is not a hazard at all. Hazards happen only when there is a write involved. And the only kind of data hazards which happen in the MIPS pipeline are read after write hazards. Well, it turns out that not all read after write hazards in the MIPS pipeline can be avoided through data forwarding. There is one case which does require a stall. This case is illustrated in this example. Here we are loading the value of R1 in one instruction, and in the very next instruction that value is used. So if we draw the pipeline timing diagram, we see that in clock cycle number 4, at the end of clock cycle number 4 is when the value of R1 is available, but it is needed for computation in the subsequent instruction at the beginning of clock cycle number 4 itself. So even with forwarding, this situation will lead to a wrong result. That is, this data dependence cannot be resolved without using a stall. So assuming that we have the necessary data forwarding, how many cycles of stall will be required to handle this situation? And after the stall, what exactly is the data forwarding which will come into play? Well, we will require a stall of 1 cycle, and after the stall, we can forward the data from the MEM write back latch to in front of ALU where it is required for the add instruction. Well, we have been pushing all kinds of details under the carpet. All of this data forwarding and stalling require control logic, and this is going to be quite complicated, and all this data forwarding and stalling is one of the main reasons for complexity in control in the pipelined MIPS implementation. Now here is a neat thing which will put together what you learn in this computer architecture course with what you will learn in a compiler's course. Let us take this simple example of higher level language code which involves A equal to B plus C followed by D equals E plus F. A regular or naive compiler will produce code which looks something like this. We load the value of B onto a register R1, load the value of C onto another register R2, add those two values onto another register R4 and store the resultant value onto the memory location corresponding to A. So this code here is not quite MIPS or deluxe code. It's a kind of a pseudo assembly language code. Just like this set of 4 instructions for A equal to B plus C, we have another set of 4 instructions for D equal to E plus F. Focus here on what will happen because of data dependence, how many pipeline stalls will happen because of data dependence in this sequence of instructions. Well, we will have one stall due to This load word followed immediately by an add instruction which uses this value R2 due to this data dependence. Likewise, we will have another stall because we are using this add instruction reading value R1 which was produced by a load word instruction just before it. Now, can you be clever and rearrange the order of instructions such that in the pipeline these two stalls are avoided? Of course, the new code should produce the same end result as the original code. It is quite simple actually. We just have to rearrange a couple of instructions so that there is a gap of one instruction between the dependent load word and add instructions. So this was the dependence which caused the stall earlier. We have removed that dependence by introducing another instruction in between which would have executed anyway later on. So just because we have moved this another load word instruction beforehand, the logic has not changed. We have just avoided one stall. Likewise, by inserting this store word instruction in between this load word and add, we have avoided a pipeline stall. So just by using some clever code scheduling, this is known as code scheduling, rearranging of instructions to produce the same result but by avoiding stalls at the same time. By this clever code scheduling, we have avoided those two stalls. If we did not have clever code scheduling, the CPI would have been increased beyond the ideal value of 1. It would have been 1 plus the fraction of loads which cause stalls. If you remember many lectures back, I had mentioned that compiler plays an important role in determining the CPI of the program which is running. Here is a very clear-cut example of how the CPI can be affected by the compiler's role in clever scheduling. Speaking of dependencies, isn't it exciting to see that there is this kind of dependence across what you learn in one course and what you learn in another? To summarize, we saw that data hazards are nothing but dependence of data across different instructions in a program. This is something natural in any program. In MIPS, we saw that only the RAW read after write dependence, RAW hazard, is possible and only in registers and not in memory locations. Still, we can have a stall if there is a load word followed by a dependent instruction. Of course, there is a need for control logic for determining when data forwarding is required, where data forwarding is required, and also when stalling is required, how many stalls are required, and so on. How this control logic is achieved is a topic for a later video.